Hello, everyone. Welcome to another session of Math and Hep Theory seminar. Today, we're happy to have Professor Satoshi Nawata to give us a talk. Satoshi Nawata is an assistant professor at Fudan University in Shanghai. He obtained his PhD degree at the University of Wisconsin-Milwaukee. Following this, he held several postdoctoral positions at the University of Wisconsin-Milwaukee, the Tata Institute of Fundamental Research, the Perimeter Institute, the National Institute of Subatomic Physics, and Caltech. His interest lies in mathematical physics, topological quantum field theory, and the statistical aspect of supersymmetric theories and string theory. We are happy to have him to giving the talk Branes and the double affine Hecke algebras and representations. Now I will hand the conference to Professor Satoshi Nawata. Thanks for accepting our invitation.
Thanks for the nice introduction. Thanks for the invitation. And then thanks to the audience for joining this online talk while during the string month. So today I'm going to talk about some joint work with Sergei Gukov, Peter Korolev, and Dupay and Saberi, Ingmar Saberi, which appeared 2 years ago. But I'm doing some related work recently, which ongoing work. So that's why and also I think this talk is very suitable for 2 hours. So yeah. So I'm going to talk about the Branes and the Daha representation. So today's talk is really the intersection between geometry and algebra and then physics. And today's talk is really intersection. So first I'm going to talk about the 2D air model or 2D single model whose target is some Hitch modular space. And from there, using air model, we use the deformation quantization and this called Brane quantization to get the Daha and its representation. In second, I'm going to move on to try to connect the Daha representation to 3D physics. And then 3D physics is related to some modular tensor category arising from the minimal model of WN algebra. And then at the end, I'm going to talk about the Fourier two-star. I try to connect Daha with the Fourier two-star theory, which is related to the Coulomb branch geometry of Fourier two-star theory and its relation between the Hitching modular space. So really the mixture of the geometry, algebra, and physics. So if you have any questions, please let me know. In the first half of the first 1 hour, I'm gonna talk about the 2D air model as I mentioned. In particular, whose target space is so-called 2D air model, whose target is the modular space for Lie connection over the once functional torus. Structure group is SL2C. And then in particular, we consider the so-called the boundary condition in A model, which is described by A-Brane. And in particular, we try to consider the category of the A-Brane, so entire category of A-Brane. And then we want to show that some solid evidence that is equivalent to the representation category of so-called double affine Hecke algebra. I will explain what SH dot double dot means. In this talk, I talk about the denote Daha is H double dot, and SH double dot is so-called spherical subalgebra, which I'm going to explain more in detail later. And then the later half of the talk is the, as I mentioned, 3D modularity and the Fourier two-star theory. That's the plan. Okay. And then let's start with the 2D air model. Before going to the 2D air model, first let me briefly introduce the algebra side. So in this talk, we switch algebra, geometry, and physics are like very freely. So the first, but let me introduce our main character Daha and representation. So Daha was introduced by Cherek in mid-90s to introduce that it's better to first consider so-called orbifold fundamental group of the so-called T2 mod point over Z2. So the torus is the, so you just consider the universal covering of torus, and you just identify top and bottom, and then side and side, you get torus. And then you put the once function torus, once function, so you just get rid of once torus, and then you just identify Z2. So if you have the Z2 element, it's really the, you have this universal covering, you just identify the X and the minus X around the origin. That's a Z2 action we consider. If you consider such a space, and one can consider so-called a fundamental group, more precisely orbifold fundamental group, because we just have this so-called Z2 action, and then they are generated by so-called X and Y and T. So X is the generator of meridian or A cycle of torus. Y is the generator of the B cycle or like a longitude of a torus. Okay, so if you have a torus, this is X, and Y is this one. And since there is a Z2 action, this point and this point is identified because of the they're related by the minus sign. So therefore, so here we just consider that this point and this point is identified. So therefore, this is actually also the generator of the fundamental group. And so they are generated by this Txy, and there is some non-trivial relation between them. So for instance, here you have T square, and you have T square, X and Y, X inverse, Y inverse. One can have such is equal to trivial because it's just contractible. And another thing is T, and once you take a T, so the direction of X and Y arrow will become opposite. So T, X, that will give you trivial one. And the other is T, and then here is Y inverse because the direction arrow is becomes opposite once you take the T first. So T, Y inverse, T, Y, that's also contractible. So this is another relation. So that's orbifold fundamental group of this space. And that's how it can be obtained by deforming this relation and adding so-called Hecke relation. So T, so this T is some kind of generator for Z2. So therefore Z2 is T squared equal to 1. So that's the actually Y group element of SL2. You just add this one and deform it by so-called small parameter T. This is just some deformation parameters. So once you take small t is equal to 1, this becomes T squared equal to 1. So that's Z2 element. But once you introduce non-trivial parameter T, this is called Hecke relation. And so therefore, this Hecke algebra is the deformation Y group algebra. In addition to that, you just deform this Bru relation by introducing another parameter Q, which is commutative with any element. And the other relation is the state as it is from this orbifold fundamental Daha. So why is it called double affine Hecke algebra? Hecke relation is this one. It's called Hecke algebra, which is the deformation Y group algebra. And you add the two affinizations. So this relation is called affinization of T element. This T is a generator of Hecke algebra. And then this X and Y is sometimes called a polynomial generator, which become clear. The Y is called polynomial. But anyway, so these two direction is the affinization. So essentially this torus A cycle and a B cycle element is the affinization of the Hecke algebra. since two directional optimization. That's why it's called double affine Hecke algebra. And then x and y and t are related by this this relation. And so the q and t is q and the small t are the information parameter. That's the SL2 double affine Hecke algebra, and I just call it H double dot. Any question at this moment? Feel free to ask question if you have. Let me move on. So let's consider the symmetry of this double affine Hecke algebra. So as you consider the origin of this double affine Hecke algebra, which is the open fundamental group of one function torus or Z2. So therefore, it's natural to imagine the SL2Z action as an automorphism on the double affine Hecke algebra. That's the case. This, for instance, this tau plus is actually 1, 1, 0, 1. It's a familiar T element in SL2Z. Which map the y is the xy, okay, and the other element, and tau minus is indeed 1, 0, 1, 1. So therefore, the x is mapped to yx with some deformation parameter. Sigma is indeed 0, 1, minus 1, 0. Okay, so that's so therefore x and y are swapped like this way. So x goes to y inverse and y goes to x with some correction. So that's the one automorphism of the Daha. So another automorphism is something very simple, which is just flip the sign of x, and then x goes to minus x, which I call x(c1), x(c2) is y goes to minus 1. Sign change, sign flip generator. So therefore, this is C is indeed z2 cross z2. Indeed. Since even though it's very simple, later if you in entire talk, they play a very important role, this symmetry. So keep it in mind. And as I mentioned, so the Daha has some important subalgebra called spherical subalgebra, which is in physics language the gauge invariant part of the subalgebra. To define that, we introduce so-called idempotent, which is the this one, capital T plus small t inverse and over small t plus small t inverse. And if you use this Hecke relation, one can show that the E square is equal to E. So E square is equal to E. That's easy to show. And this relation is called idempotent. And this spherical subalgebra is indeed can be defined by just sandwiching double affine Hecke algebra by this idempotent element. Okay? And in particular, so the small x is exe with some number, some certain normalization, and small y is the e capital Y e. Okay? And essentially, if you do that, I do the computation relation between use the t and the x, one can obtain just it can be written x plus x inverse times e, y plus y inverse e. And the other this spherical Daha, I call it spherical Daha, is indeed generated by three generators, the other or two generators, x and y, but it's natural to introduce some z variable, which is just a q commutator of x and y. Q commutator is given by a q minus 1/2 xy minus q 1/2 yx. So that's a q commutator here. And to get the and then you get the z, and then you do the same cyclic condition for computation relation. Okay. And another important relation is this guy. So I call it the Casimir element. Since if you take this combination, the right-hand side is only written by small q, small t parameter, which is a deformation parameter. So therefore, right-hand side commit with any element of x, y, z. Okay, x, y, z. So therefore, they commit with any element. That's why it's called the Casimir operator central element. Any question at this moment? So these are the spherical subalgebra of Daha. I call it spherical Daha, generated by x, y, z, and they're related by the relation given by here. Any question at this moment? Then we can move on we can move on to connect the geometry. Once you take small q goes to one limit, one can easily connect the geometry. Once you take q go to one limit, this relation, everything goes to 0. Right-hand side becomes 0 because q inverse minus q is equal to 0. So therefore, x and y are all become commutative. Okay, it's a commutative algebra. And then what's left is the relation between x and y and z. That relation is given here. So this is indeed describes so-called modular space of SA2C flat connection over the one puncture torus. So this is indeed a complex two-dimensional affine variety. There are some questions in the chat. Is there a relation between symmetry group you wrote and the spherical part? That's I'm going to talk about in here, so don't worry about it. So the x, y, z are the parameter of the C3, and this relation will cut out the complex two-dimensional affine variety. And then this T is actually monodromy, SA2C monodromy parameter along this puncture. So therefore, monodromy matrix is given by this here. And if you take a trace of this one, you get the monodromy t squared plus t to the minus 2. And in fact, this x and y and z, just if you consider origin, so this is indeed a SA2C holonomy of meridian. So therefore, it should be trace of x and x inverse, which is small x. But likewise, trace of y, the capital Y, y inverse is small y, which is the holonomy of the longitude or B cycle. And the z is indeed essentially the diagonal one. So x and y, holonomy of x, y, and z is the diagonal one. And then if you look at if you consider the SA2C metrics between them, they satisfy this relation. And this describes the modular space of SA2C flat connection. Therefore, the spherical subalgebra is indeed deformation quantization. It becomes, once you introduce Q, it becomes quantized in terms of some particular simplex form. I'm going to explain later, some holomorphic simplex form. In terms, one can do the deformation quantization, and a commutative algebra become non-commutative algebra but after the deformation quantization. So therefore, the spherical Daha is indeed the deformation quantization modular space connection over the one small torus. This was shown by Blankov. And then, as you can easily see from this geometry, so it received a so when the Sebastian asked was so PSL2Z times this Z2 times C2 acts on the spherical Daha as follows. So y goes to y is moved to y and z are swapped essentially like this way. So this T transformation y goes to z position like this way, and the tau minus is equal to 1, 0, 1, 1. That is the x is moved to this part, and then z is go to here, and so on. And then sign flip transformation is very easy. So you just put the minus and negative sign in front of a small x. But since we know that the x and y z is coming from commutator of x and y, so therefore natural consequence is the negative sign in front of z for c one element. Likewise, you put the negative sign properly for c2 and c3. C3 is indeed c1 times c2. They commit, so it doesn't matter. So that's so the PSA2Z times C is indeed a symmetry of the spherical Daha. Okay. So any question at this moment? Okay, then let me move on to the next. So from now, I'm going to talk about, I'm going to discuss the representation theory of the spherical Daha from geometry. But before moving on to geometry, we just look at the algebraic side. So the Daha indeed arises from the study of the Macdonald polynomial by Chernik. Therefore, it acts somehow on the naturally acts on the Macdonald polynomial nicely, and then which is called a polynomial representation. So Macdonald polynomial is indeed the so-called ring of symmetric function with some rational function of the Q and T coefficient. And X is mapped to, as you can easily guess, capital X plus X inverse. In fact, the ring of symmetric function means Z2 acts as the X goes to minus X. So all the polynomial is invariant under this Z2 action. So therefore, the capital X plus X inverse, because it's a meridian, as I mentioned around here. So a trace of the holonomy. So therefore, it just comes with the symmetric way, X and X inverse. And then more importantly, Y is mapped to so-called difference operator, which is called Macdonald difference operator. And in fact, this under the polynomial representation, it acts as whose eigenvalue is indeed the Macdonald polynomial. So since SL2, we consider SL2 Daha. So the Macdonald polynomial is labeled by the representation SL2, which is the spin J representation. So the J boxes here. So and I just write down the number box J here. And the Macdonald polynomial is the eigenfunction of the Y under polynomial representation, and the eigenvalue is written here. And then action of Z is naturally come from the Q commutator X and Y, which can be written like this. So this guy is indeed acts as a difference operator. Capital X is Q times X N, like this. So difference operator. So and then this Macdonald polynomial is labeled by J, and the J runs for 0 to infinity. That span is the basis of the ring of symmetric function with coefficient on the rational function Q and T. The representation can be studied by just constructing so-called raising and lowering operator, which just increase the number of boxes of the Macdonald polynomial. Raising operator, which is generally written by small x and small z with some coefficient. Lowering operator also written in terms of x and z with different coefficient. And then it just reduces number of boxes in Macdonald polynomial with some coefficient. And using this one can study the representation theory in detail, but which I'm not going to go into the detail. But the important thing is so this coefficient becomes 0. So lowering of operator analysis P is something called finite dimensional representation here. So as I mentioned, so raising operator increase the number of boxes like this way. Lowering operator decrease number of boxes on Macdonald polynomial. And this raising operator never becomes 0. Never becomes 0. So, but the lowering operator can become 0 when this coefficient becomes 0. If this is the case, we can just have so-called idea. Also, this part is annihilated. So therefore, you get the finite dimensional representation spanned by finite many Macdonald polynomials. So this is called ideal. Ideal is essentially the place the lowering operator becomes 0. It's called null vector. And you just get rid of this infinite many part, and then what's left finite part is a finite dimensional representation of spherical Daha. So if you know about the Biot algebra and the representation, this polynomial representation can be understood as a Bernoulli module. And then this, once you set some particular condition, this become a new vector or new state, and you just get rid of the ideal generated by the new vector. And then, as I mentioned, so if you focus on this coefficient, so I just zoom in. This coefficient is written by here, and then when q to the 2n is equal to 1, this part is becomes 0. So therefore, one finite dimensional representation appear. This is the dimension. And then for the second part is t squared is equal to minus q to the minus k is appear when this part is become 0. Okay, so therefore another finite dimensional representation show up. And for this part, when this part equal to 0, you have to be careful because I mean here in denominator there is something even times t squared up here. So therefore we want to avoid the denominator because 0. So therefore here j has to be j minus 1 has to be odd. So if you add this condition, so if you t squared is equal to q to some minus odd number, then this time becomes 0, and this is stay the finite part. Then you will get another finite dimensional representation. So under these three conditions, and then each of condition will give rise to different finite dimensional representation. And if we will construct these finite dimensional representation out of the modular space or SL2C Flock function over one punctual torus from now on. Any question at this moment? Is it coincidence that Daha gives the modular space Flock connection? Daha gives the. Is there a reason for that? There are lots of reasons for that. I mean, that's the origin. I mean, Sprague Daha is indeed a deformation quantization of T mod W, and this T is coming from X. We give rise to X generator, and the other T give you Y generator, and then mod W is some Sprague part. And the T cross T mod W is indeed a modular space of Flock connection over torus. And if you deform it, you get the Sprague Daha. So it's very, very natural to get the Daha out of modular space of Flock connection. Any other questions? If not, so we will construct these finite dimensional representation from geometric from now. To approach the representation theory from the geometry, one can use so-called Branes quantization. Branes quantization is indeed some bridges between the so-called deformation quantization, which gives rise to algebra, and the geometric quantization, which gives you Hilbert space or vector space or representation. They are all same, which I'm going to explain in detail in next few slides. And this was invented by Gukov and Witten in the 2008. So the geometry we're targeting is of course, this SL2C Flock connection over the one function torus. But it's well known that this is diffeomorphic to so-called Hitch modular space over SU2. Hitch modular space is indeed a homomorphic rank 2 vector bundle with some so-called Higgs field, which takes some endomorphism of E times the canonical bundle over the base curve, or base curve means the one function torus. And with additional, it's called Hitch equation, which is some kind of stability condition, but I'm not gonna go into the detail. But in any case, there are two ways of describe this our target space or target space. One is the SL2C connection, and the other is so-called Hitch modular space. And the deformation is called non-abelian Hodge correspondence and so on. And in fact, there hyperkähler manifold. Hyperkähler manifold have a three distinguished complex structure, I, J, K. They satisfy some kind of coordinate relation. And the choice of these three distinct complex structure is as follows. Standard notation is this complex structure I is coming from this complex structure of the base curve, once function torus. And for complex structure J, is really coming from complex structure coming from SL2C. So I is essentially coming from this heating side, J is coming from this flat connection side, and if I times J will give you the K. And then what's the meaning of this complex structure J coming from this SL2C means that it's kept small x and small y and small c as a holonomy of SL2C. So therefore, small x and small y and small z are holomorphic with respect to this complex structure J. But if you look at from different complex, for instance, I and K, they're no longer holomorphic. Okay. So that's the case. And then the formation quantization of this space will give you the spherical data. But to describe the deformation quantization, you have to specify so-called holomorphic symplectic form. And a homomorphic symplectic form is indeed, we pick with respect to J, which is the small omega K plus I times small omega I. So each complex you can associate the so-called Kähler form, omega I, omega J, omega K. And then we pick particular combination of small omega K plus I, omega I will give you capital omega J. And which is written by dx wedge dy over 2z minus xy. So everything written in terms of xyz. And if you do the deformation quantization omega j, you get our desired spherical data. To see geometry more explicitly, the small t goes to one limit, and the q goes to, of course, one limit. In fact, it's just a SL2C flat function of just torus. No puncture. So therefore, as I mentioned, this holonomy. So the SL2C holonomy of mu is indeed takes the x minus x inverse. Here is the meridian, and longitude is y minus y inverse. And if you take the trace of mu, you get the small x. And trace of lambda, you get the small y, and they satisfy this duration. Now, B is just a trivial 1, 1, 0, 1, 0, 0, 1. It's just an identity matrix. And that is the SL2C production function with torus, without puncture. And that is exactly in fact, the C star cross C star mod Z2. One C star is spanned by capital X. The other C star is spanned by capital Y. And then there's a Y group action acts on simultaneously X and Y, capital X and Y. So that's the SL2C function over torus. And if you look at the real locus, which is the flat function of the structure group SU2, C star is essentially the C mod get rid of puncture, and the real locus is S1 here. C star, real locus S1. Which is the carton of SU2, and S1 cross S1 is indeed a real locus of C star cross C2 star, and then D2 action acts naturally. So this is a real locus of flat connection. So therefore, this is indeed T2 mod Z2. So if you look at the torus, it's identified by obtained by just identify top and bottom and side, and Z2 acts on the opposite side, as I mentioned. So therefore, at the end of the Z2 action, this becomes a so-called pillow case. It's called pillow case. There's a full torsion point or like a singular point after Z2 action, but it looked like a pillow case. So and there's a full torsion point. So this is a story when small t is equal to 1. Okay? So therefore, there's a full singular point in a surface or this our target geometry. So once you axons turn on small t, the geometry is slightly modified. If you turn on the ramification, I call it the ramification. This capital A is a connection of the Higgs bundle. Higgs bundle is this E, and then this phi is a Higgs field. Can have this some monodromy along this puncture, and a small t is indeed can be written in terms of this alpha and gamma. Alpha and gamma can be. Okay. So that's the deformation parameter holomorphic in complex structure J. Okay. So there's a complex structure parameter in terms of J. And then once you turn on let's turn on alpha, only alpha, and then let's forget about beta and gamma at this moment. Beta and gamma equal to 0. Then this, as I mentioned, this pillowcase is indeed sits into this so-called hitching, the center hitching vibration, and it becomes smooth. The pillowcase is modified as so-called this singular 4-point is from out of it one can get some divisor or like S2 will show up once you turn on alpha. So that how does hitching vibration works? So this hitching vibration is the modular space of Higgs bundle. Higgs bundle to the trace of this phi square. So this is trace of phi is a Higgs field. So you can just have projection, and each pick the point in the it's called hitching base trace of phi square. Pick a point, its pre-image is indeed it becomes torus. So that's why it's called complete integrable system. So it's algebraic integral system. So that the each for generic this hitching vibration is indeed some kind of torus, Lagrangian torus. Lagrangian with respect to omega k. I will explain omega k is associated to this k, which I'm going to explain more in detail. And then this without turning on any puncture, this if you look at the origin pre-image of the origin under the hitching vibration, this really bound this modular space of SU2 Flack function lives in this pre-image of the origin of the hitching vibration. So without T or alpha, without alpha, alpha is equal to 0, it's just some pillowcase. But if you turn on the the alpha, the geometry becomes smooth. It's called the stable Higgs bundle. And then the S2 will show up. So this looks like a affine default Dinkin diagram. So therefore affine default singularity, or so these are the torus vibration or elliptic vibration is called, and the elliptic vibration singular fiber is classified Kodaira. In the Kodaira classification, it's called I0 star. Okay. So this form of look like I0 star. And in my notation, this generic fiber, which is torus elliptic vibration, elliptic curve, which means is I call it F. I call F fiber, and then I call the middle element is called I call capital B, or like people call band G. Band G is the band G is I call it B, or like it's the same modular space of SL2, SU2 Flack connection. So real locus. And then D1, D2, D3, D4 show up after alpha is turned on. That's called so-called exceptional divisor. So that's an exceptional divisor. Show up after turn off. So far, is a story is beta is equal to gamma equal to 0 part. So the geometry is still a bit simple. Any question at this moment? So the homology class, so this is S2, there is a 5S2 in the geometry. So they found the second homology class of the Hitch modular space. And then this fiber is also second element or second homology, but there is some non-trivial relation between in homology. This the F is indeed the generic fiber is the homologically equivalent to 2 times band G, plus all the exception divisor. So you have a which means that if the generic fiber is degenerate to this in the center, so you just wrap all the exception divisor, and for band G or B, there are 2 times it wraps 2 times once you degenerate. So that's a relation between F and B and Di. Okay, is there no other type of singularity except D4? I mean, in the once function of torus, I'm going to explain. So once you turn on beta and gamma, the vibration is drastically different. So this middle, this singular fiber is split into 3 parts. So there is 3 parts. It just split in 3 parts once you turn on beta and gamma. Beta and gamma ramification parameter Higgs field. So these are the singular fiber which called I2 because it's just look like a 2 banana connection. This is I2 affine thinking diagram, A2 affine thinking diagram. I2 singularity. So the once you turn on beta and gamma, singular fiber is it's totally different. And then the homology relation between so that I call it the irreducible component. I call it this is each irreducible component is banana, but it looks like banana. So there are 6 banana in a Hitch modular space, and then these 6 banana have the homological relation between all previous 5 sphere with this relation. And then moreover, more interestingly, as I mentioned, this geometry receive SL2Z times C2 action, and SL2Z indeed swap. So this is tau plus 1101 element swaps these 2 exceptional divide. Sorry, singular fiber, and then the other tau minus swap these singular fiber, and the sigma swaps these 2 fiber. And in previous case, as you can guess, so the SL2Z actually is invariant. This middle guy is invariant at SL2Z, but the tau plus will swap these two, and tau minus. Sorry, tau plus is swap these 2. Tau plus swap these 2, and then this tau minus swap these 2, and sigma will swap these 2. As you can easily see, because it's it used to be how to say pillowcase T2 mod Z2. So if you consider the origin of the torus, you can just easily see that how the SL2Z acts on this I0 star quadrilateral singular fiber. And then SL2Z is under this guy, and this guy is invariant under SL2Z as a set. Okay, like this. Those are the geometry of the exceptional combined. So now I want to connect is the homology relation easy to see? Good question. So this homology relation is indeed coming from the affine D4 Carter matrix 2, 2, 2, 2, minus 1, minus 1, minus 1, minus 1, minus 1, minus. Anyway, so it's just coming from this affine thinking diagram. And it's just coming from here, and you just look at the null element. You can get this homology relation. And for this guy, homology relation, you really need to work hard on this so-called Mayer-Beatrice long exact sequence of homology. This is need hard work, actually, hard work. Okay, so now we set up the algebra and geometry. We try to connect between these 2 by using Branes quantization. So the Branes quantization is indeed a 2-dimensional sigma model whose target is this modulus Flack function. It's a Flack function of a one function torus. And then in particular, we do the so-called A twist. So therefore, A model is indeed we just look at the target as a symplectic symplectic geometry. So that it's even though it's a hyperkähler, we pick particular symplectic form and consider a model with respect to this particular symplectic form. And then, so it's a sigma model. So therefore, you just have some Riemann surface. The Riemann surface we can have a boundary, and it's mapped to the this MH or M flat. It's just mapped to here, and you need to specify this boundary condition on the boundary. So, and the boundary condition is specified so-called A-brane or Lagrangian brane. So, usual A-brane is the support is Lagrangian inside of this target, and then with particular symplectic form, and you just consider so-called unitary flat bundle. Okay, flat bundle of a unitary function, or people call sometimes called local system. However, the Kapustin-Orlov showed that this time A-branes are supported so-called higher dimensional submanifold. Lagrangian submanifold is indeed if the symplectic manifold is 2-dimensional, Lagrangian submanifold is dimension n. But co-isolated submanifold is indeed specifies some Poisson commuting function f1 dot fi is equal to 0. So f1 is equal to 0, f2 equal to 0, fi is equal to 0. They are all Poisson commuting. fi and fj are Poisson commuting. So this, so the equations cuts out the some manifold, and then if all the if you have n Poisson commuting function, this would describe Lagrangian submanifold, but it can be high dimensional. And there's one distinguished object called canonical coisoc brane. So that is some canonical boundary condition in a model. So that was found by Kapustin-Orlov, and whose the support is the target geometry itself. So it can end any point in the sigma can end at any point in the target space. But the more interesting, more importantly, so one has to consider so-called line bundle whose curvature satisfies this following condition. Whose curvature, real part, the curvature is specified, curvature is corrected by B field in the sigma model, is the, in fact, real part of this holomorphic simplex form scaled by IH bar. Okay? This H bar will show up in the deformation quantization. So so this brane quantization first connect deformation quantization and geometry quantization. So deformation quantization will give you algebra, and the geometry quantization give you Hilbert space or Hilbert space, and the algebra acts on Hilbert space that will give you representation. And to give first the deformation quantization, this canonical brane, coisoc brane, I call it BCC. Canonical coisoc brane plays a very important role. So the deformation quantization, we introduce Q. So therefore, you have to introduce some kind of Q parameter, and whose log is essentially Q is equal to e to the 2 pi I h bar, and the h bar appear here. Okay, and you scale the holomorphic simplex form omega j, and the just real part of it is f curvature plus correct by B, and then imaginary part of this part is indeed simplex form we consider here. And if you consider the the so-called BCC string, so if you consider the strip with the boundary condition, so the strip with boundary condition BCC, that can actually form the so-called algebra. If you just consider this kind of strip, and you put the BCC, then the algebra here is just give you some, is the product of this element will give you another element in BCC string. So therefore, this BCC string will form the algebra, and the product is really coming from this margin of the strip. It's just margin of strip will give you for instance, if you have an x and a y, you get the x times y and so on. So that will give you so-called deformation quantization of the holomorphic function over this target space. So since our target space is modulus of holomorphic Flock function, so BCC string will give rise to spherical Dach. Okay. To get the representation, we will use so-called German quantization that will give you Hilbert space. To get the Hilbert space, we have to use the other boundary condition. That is a really ordinary A-brane, I explained. Ordinary brane is Lagrangian brane. So therefore, once you have the BCC-BL strip, and you can merge with BCC-BCC strip, and you get another BCC-BL. Okay. So therefore, BCC-BL strip is indeed by joining BCC-BCC strip, you get another BCC-BL. So therefore, this becomes representation. So it's action of a spherical Dach. So therefore, given a Lagrangian brane, Lagrangian A-brane, you get the corresponding representation of the spherical Dach. So therefore, it's very natural to think this Lagrangian brane is a corresponding module. Therefore, it's natural to expect the A-brane, there's a one-to-one correspondence to A-brane and the representation of the spherical Dach. So that's why the brane quantization is just give you the deformation quantization and German quantization, and in the package, and then the byproduct we will get the representation too. In terms, you can just construct representation in terms of geometry of the target space or Lagrangian brane on the target space. So that's a deformation brane quantization introduced by Google with. Any question at this moment? Oh, there is some question in the chat. Oh no. Any question at this moment? That's sorry. Does this BCC brane correspond to some particular SUSY brane in 2A? I will explain how to connect the BCC brane to the some higher dimensional string theory later. So you should wait. It's really comes the end of the second half of the talk. Now, so once this Lagrangian submanifold is a compact, then corresponding brane become finite dimensional module. Okay. So again, so as you recall, so we can construct finite dimensional module out of polynomial representation once we impose some condition on small q and small t. This finite dimensional representation, so we want to see some compact support brane out of the geometry. That's what I'm going to see. And to get the dimension of the module or representation, one has to use so-called Riemann-Loch, here's the Riemann-Loch formula for this brane. It's actually, brane is come from some bundle and the connection bundle. So this line bundle, BCC comes from line bundle, and Lagrangian brane also come from flat unit bundle. So therefore, one can just construct so-called historical Riemann-Loch to get the some Hilbert space. This is really coming. It's the German quantization to get the space of Hilbert space coming from German quantization. One can use Hilbert Riemann-Loch. I'm gonna skip detail. I'm gonna skip detail. Solution. I understand how it is easy to construct Lagrangian side, but is it easy to construct Lagrangian Flock connection side? I understand how it is easy to construct Lagrangian Higgs boundary using Lagrangian H library. Okay, but is it easy to? Yes, I mean, for instance, Flock connection, it's not compact, but for instance, it's flat of the sigma can just have Lagrangian submanifold for a flat of M3. So a boundary M3 is equal to sigma. So for instance, this is the so-called ABA brane. ABA means Lagrangian with respect to I and K. So this is really coming from if you consider M3 and with the torus boundary and so on, M3, And that, if you consider flat connection over M3, that will cut out some, anyway, ABA brane. And then most likely, and also, like, there's also Oper and so on. I think Nikita or like whatever, whoever, Gayato talk about this kind of stuff in the string mass talk. I guess this Oper bright is also some Lagrangian. So now we want to compare finite dimensional representation here and the compact Lagrangian brane here. So to do that, firstly, call that this generic fiber. You have a generic fiber. So this is indeed a algebraic integrals and Higgs bundle. So therefore, it's the how to say? It's the Lagrangian with respect to omega k. Okay. And then omega k. So therefore, so it's a compact, right? Torus is compact Riemann surface. So therefore, it gives rise to some finite dimensional module. So this becomes this becomes Lagrangian when this omega x is omega k, and then f is equal to omega I. Okay. So therefore, this one h bar has to be some real number to get the correct Lagrangian brane condition of this one. In fact, this h bar, when you set h bar is equal to 1 over 2n, then you get the first shortening condition we encounter from polynomial representation. And in fact, this, sorry, I just somehow moved. This compact brane, I don't know why. Sorry, wait a sec. So this generic fiber is indeed the finite dimensional representation coming from this first shortening condition we encounter from polynomial representation. And in fact, so it's come from a local system of flat connections. So therefore, you can have holonomy of the meridian and longitude. And in fact, this meridian holonomy is some parameter, just parameter that inside a finite dimensional representation. You can have some parameter. And also this Hitchin vibration, you have a 6 banana. And in fact, this one banana can be compact brane or with respect to omega k. And in fact, this one, guys, also arises once you set this condition. And this is indeed coming. This will give us another finite dimensional rotation corresponding this U1. And in fact, so as you can see, this F can degenerate to this singular fiber, which splits into U1 and U2. And in fact, it looks like it splits into U2, but it's never split. It just becomes form a shorter exact sequence. So therefore, so this generic fiber brane degenerates into this singular fiber. It gives rise to some compound, it composes some bound state of brane with respect to U1 and U2. And in representation theory side, we can also see the some short exact sequence of finite dimensional representation. So therefore, you can easily see how this representation, finite dimensional representation, and then the compact brane are one-to-one corresponding. Okay. Anyway, so since this one is trivial cycle in here, so you have to set some holonomy to vanish. This is -1 condition. So we can see that the similar condition thing in the, so once you set the beta goes to gamma equal to 0, then essentially so the singular fiber is the I0 star or affine default thinking diagram. And then in order for this middle guy, I call it Banjio or like capital B, to be Lagrangian, we have to impose this kind of condition. T squared is equal to -Q3 minus Q3 minus K. So this is indeed the second shortening condition we encounter in the polynomial representation. So therefore, so this guy is indeed correspond to finite dimensional representation coming from second second shortening condition. And then the third quantum, as you can easily guess, the third shortening condition, it really comes from the when this exceptional divisor become Lagrangian submanifold. So once you set the condition that these exceptional divisor become Lagrangian, this is exactly equal to t squared q0 minus odd number. And so therefore, there's a one-to-one correspondence between finite dimensional representation, irreducible representation, and then the finite compact Lagrangian brane in Hitching vibration. So what's nice about this one of the geometric approach is indeed one can find a new representation. For instance, if you consider the brane supported also for instance, consider supported on these one capital B and the three exceptional divisor. This Lagrangian brane give you the some finite dimensional representation, which cannot be captured by quotient of polynomial representation. But if you look at the morphism structure of the representation theory side, in fact, there's a corresponding finite dimensional representation corresponding to this strange Mickey Mouse. And so therefore, if you compare with the geometry by using brane quantization, we can find a new representation, and we can understand the representation geometrically. And also, there's something like a kind of new phenomena. For instance, this F is moved to this direction through the two way of degeneration. One is the since I'm not going to go into detail. So morphism structure. So the intersection between U1 and U2 have a 2 point that will give you two-dimensional x to 1 so-called extension. So there are two short exact sequences will show up in finite dimensional representation theory. And it's kind of like a new phenomena in A-brane, even though support is the same. Support is the same. There are two different objects in the Fudan category or A-brane category. So therefore, the geometric approach will give you some nice way of looking at the geometry, nice way of looking at representation data in terms of geometry. So this is the first half of the story. So any question at this moment? Do you need a short break? I think it's a good time to take a break.
Sure.
Okay. So we will move on to, so we finished the story of 2D and story and then move on to 3D and 4D story in physics side. So now we consider the 3D modularity. So we try to connect the 2D story we discussed in the first half and lift it to the high dimensional physics. And as you can easily guess from the title, so we focus on this. Oh, sorry, like this. So we focus on this PSHE action on a modular space of Lie connection and this Sprague-Daha. We know that Sprague-Daha and target space enjoy the SL2Z action. In particular, some compact plane enjoy SL2Z, as I mentioned. So this default singular fiber is a singular fiber. It's the resolution of this pillowcase, which is T2 on Z2. So therefore, this guy and this guy is invariant under the SL2Z or other set. So it's just other set. So therefore, the representation theory coming from this B1 and B, so which I listed here, And Joe is also PSA2Z action. So they are invariant, receive the action PSA2Z. So these are Hilbert space, as I mentioned, coming from general quantization. So Hilbert space, some vector space is receive a PSA2Z action, which means that this is some modular representation. And then what kind of representation it is the question. And this can be answered from 3D physics. So we try to connect 2D physics and 3D physics. To connect that, one can use so-called brain in 3D brain system in the 3D correspondence. So what is 3D correspondence? We consider M theory on the cotangent bundle of the 3 manifold, and you have R4 times S1. So in total 11 dimension. And then we turn on the omega background, which is the Q parameter, small q and small t. As you can easily guess, this small q and small t's that appear in Daha can be identified these omega background parameters. And you put the NM5, right, supporting on S1 cross R2, and then wrap on M3. And the 3D correspondence will tell you that the you get the complex channel Simons M3, and 3D n equal to 2 theory living on here, and the theory labeled by M3. And this the 3D n equal to 2 side, one can consider so-called since it's the supersonic theory, you can consider the so-called the index, where J1 is the rotation of this R2, and R is a U1R symmetry of n equal 2 theory, and S is indeed the sum acts geometrical as a S1 action on the fiber of the cipher manifold. So cipher manifold is essentially S1 fiber over the some surface, which allow the singular fiber. And if you consider such a partition function, one can just, for instance, once you set the M3 to be length space, this partition or index can be written like this way. And in fact, this is called McDonald measure. It's written by Kupelhammer. This is called McDonald measure, which come from this length-based geometry. And then also you have to include so-called general set function. And this the length space P is related to this. In particular, when M3 is the 3-sphere, the partition function is very simple. Set function is really this usual set function we consider, and the times McDonald measure. This is indeed really the that appear in the norm of McDonald polynomial. Well, if one can just include McDonald polynomial like this way, you get a so-called S matrix. And this in the S matrix is indeed appear in the Shakirov even before then Kirillov or Ettingov consider. So this P is indeed coming from torus with the Wilson loop inside, and the other P mu come from Wilson loop with the other solid torus, and S, if you include glue them, the solid torus together, you get the S3 with the hot link. That's why you get the S transformation. And to connect the 3D and 2D story, one can consider the following exotic compactation. So we now M5 wraps on the S1 cross R2, which is this part. And then for M3, we just consider torus cross the mapping torus, which is just to identify torus and top and bottom with the SA2Z element. C is actually SA2Z element. This is called mapping torus, which is I replace M3. And then so this is exactly 3n equal to 2 theory we'll consider as an index. And here you have a complex channel Simon. And then you just, connect the 2D theory, we just consider the following complication. First, you consider that S1 is this S1. SQ is indeed circle of this omega background. You just consider the S1 rotation along this middle axis. This is, I call it S1Q. So S1 times S1Q, you get this, if you do the complication, this part and this part, what you get is this like a strip. And at the origin, you get some boundary condition. And here you just also compact on the torus C. So therefore, this strip comes from here, and this is S1 can give you sorry. So this part is just open string coming from this here, and here this how to say, the vertical direction comes from this mapping correspond. Okay? And then here on one end you have some boundary condition come from tip of omega background. So that is indeed will give rise to BCC. Boundary condition, canonical construct brane. And for the far infinity of the R2 or disk, you get some other boundary condition I call BL, Lagrangian brane. Okay? So therefore, in 2D physics, we consider can be constructed out of this brane system of the 3D correspondence. And then the BCC come from the tip of cigar or tip of axis omega background, and infinity at the infinity or disk infinity, you get some other boundary condition. Any question at this moment? So that's a connection between 3D and 2D physics. So now, let's consider how does the PSA2Z acts on the BCC B capital V. How does this PSA2Z acts on this module coming from this middle guy? And as you recall, so this middle guy becomes Lagrangian only when this shortening condition is satisfied. And if you impose this condition on this S matrix we consider in the previous case, okay? Here, the Macdonald polynomial is labeled by the number of boxes of the single row Young tableau. So therefore, this is infinite dimensional. So it just runs from 0 to 0, 1 to any non-negative integer to infinity. Therefore, this matrix is an infinite dimensional matrix. However, once you set this shortening condition, this S matrix becomes finite dimensional matrix, and in the rank is essentially k plus 1. Once you set this t squared is equal to minus q to the minus k. So it becomes finite dimensional, which acts on this guy, this middle guy, and one can read off the t transformation too, which is this. And this ST matrix really appear so-called refined Chern-Simons, refined system theory. Refined Chern-Simons indeed the Chern-Simons which is deformed by this small t parameter. And once you set t is equal to q, it becomes ordinary Chern-Simons. And in fact, this SNT matrix is the one that appears in Chern-Simons theory, namely the WZW with the SU2 WZW with level K. And so the level K is really coming from K here, shortening condition K here. So therefore, this PSA2Z action middle guy is the PSA2Z that appear in Chern-Simons or its deformation as a refined Chern-Simons. Any question at this moment? Now, if okay, three manifold be the Genex manifold. Okay, first of all, the three manifold. So we want to study the Daha. So therefore, we want to keep small q and small t parameter omega as a background. So therefore, to keep Q and small q and small t, this M3 needs to be cipher manifold. That is because this otherwise you have to set t equal to q. That is ordinary Chern-Simons. Ordinary Chern-Simons, you can have a generic three manifold, but refined Chern-Simons, we want to have this S action, S-U1 action, S1-U1 action. In order to preserve this S-U1 action, M3 has to be cipher manifold. Yeah, but here, so for simplicity, I consider the mapping torus, but the M3 can be constructed out of solid torus by gluing, as you know, the surgery and so on. This cipher manifold can be just constructed from this surgery on the solid torus. So therefore, this is for simplicity. I pick the here mapping torus because I just want to see the explicit this torus compactification. But it can be any cipher manifold. But connection to the 2D physics is a bit more complicated in that case. Any other questions? So now, so this is already refined Chern-Simons is for so modular so SU2 flat connection, and its a German quantization will give you the torus Hilbert space. That is a well-known story from Witten in 1988, the beautiful paper. And then this small t parameter will give you some its deformation as a refined Chern-Simons. That's an ordinary story we know very well. Okay, and the SNT matrix is really acts on this torus. Now, so let's look at the SA2 interaction. This excitation divisor D1. So this is a bit more. This will give a bit more surprise to you. To see that the shortening condition for this guy is indeed given by this, the number 3 shortening condition. So once you set this condition, this guy becomes Lagrangian, and it gives rise to finite dimensional module, and that receives PSA2 interaction. Okay. So then once you set this t squared is equal to q3, I'm sorry, this I don't need squared. Sorry, this is just a 2L minus 1. Sorry. So this condition, once you set this condition, in fact, so as you can see, so using this read off the charges of this index very carefully, this Higgs field of the living on this disk is indeed, as you move along this S1 direction, is the identified by t is equal and the q3 to L minus 1 over 2. Okay, so once you go here, this Higgs field on the how to say disk receive this action, some parameter action. Just read off the charges of this Higgs field. You get this one. Once you set this equal to 1, this is equal to 1, one can identify top and bottom. Okay, top and bottom. And this condition is equivalent to the so disk, if you have a disk and it just compactify do the 1 point compactation. So you have a disk like this way, and put the 1 point and just identify them together, you get a sphere. So therefore, this infinity corresponds to this the infinity of this corresponds to this the point here in the sphere, and this this shortening condition is equivalent to the Higgs field behave like a d to the 2L minus 1 over 2. This condition is exactly same as a so-called irregular picture at in the Higgs Hitching system language. And in fact, this once you impose the irregular puncture or wild puncture, whatever you call it, it's a higher order pole. This system gives rise to so-called non-Lagrangian theory called Abdus-Sagar theory. And once you impose this condition, exactly what you get is so-called A1 even Abdus-Sagar theory. That construction is given by Danshi, and then sphere with one irregular puncture will give you the this particular just Algebra theory, and this condition at the infinity is equivalent to the shortening condition coming from this D1, in fact. So therefore, it's natural to expect something coming from PSL2Z coming from this adjust Algebra theory, and then the PSL2Z action coming from D1. And in fact, this SNT matrix coming from this infinite dimensional guy, once you set this shortening condition, again, this infinite dimensional ST matrix become finite dimensional one that acts on this module or Lagrangian, and which becomes rank L ST matrix, and whose PSL2Z action can be identified with the modular SL2Z PSL2Z action of Birasoro minimum model. So once you set this condition and look at the finite dimensional ST matrix, this is exactly the Birasoro minimum model. Actually, it's called the 2, L, whatever, Birasoro minimum, non-unitary one. And in fact, this non-unitary Birasoro minimum model is color algebra of this adjust Algebra theory. So the surprise is that so once you look at the PSA action, this extension divisor, somehow one can see the connection to the adjust Algebra theory and the minimum model. So this is some surprise coming from once you construct a 3D and 2D. Okay. And this was the first found by Kozak, Shakov, and Yan. And then we can generalize this thing to the higher rank. So we can generalize a higher rank generalization of this consideration. So again, we can see this as Sebastian asked. So if you consider as an NC flat connection, is indeed Cartan torus of essentially this is C star cross n to the n minus 1. Cartan torus divided by Weyl group action is Sn, symmetric group of the order n. Degree n, sorry. And this is x direction, this is the y direction, as I mentioned. The torus, this is the x holonomy, y holonomy, and so on. And those are the Cartan torus. And whose the real locus is indeed given by the S1 to the n minus 1. This is the Cartan torus of SUN. And then the same Weyl group action. Here we go. Okay. So therefore, and in fact, under this Weyl group action, so if you consider center of the SUN, so which is essentially e to the 2 pi I divided by n or whatever root of unity to the k, and this one, this is center of the SUN. So these are the fixed point under the Weyl group action. So therefore, this is the x direction, as I mentioned, the meridian holonomy or eigenvalue, and this is the longitude or B cycle holonomy y direction. At each direction, you have n torsion point arising from this fixed point of a symmetric group. So therefore, in total, n squared torsion point, so n times n. So there's a whatever n times n torsion point appear in the on a torus without ramification, without in a torus flat connection. But one can add the ramification and then small t parameter along you just consider the SL2C mononomy along the torus. Then these torsion out of torsion point, one can get some excitation device. It becomes the geometry becomes smooth. And then again, so this guy in the middle guy is the again PSL2C invariant. PSL2C invariant that gives us the higher rank refined Chern-Simons or Chern-Simons. However, more interesting one is something coming from this torsion point. And so analogous to this the previous story, there's the one excitation divisor which is invariant under PSL2Z in higher dimension. Analogous to this guy. Even higher dimension one can obtain. But I cannot draw precise geometry because it's high dimension. That becomes Lagrangian when t to the n, q to the m is equal to 1, and where n and m are coprime. N is a rank of structure group or whatever, gauge group, whatever call it, and m is some coprime integer. And in fact, this one can construct the S and T matrix coming from this McDonald polynomial or whatever. One can impose this condition. Again, you can have the finite dimensional matrix, S and T matrix. And in fact, once you set some Q's root of unity condition, this is in fact equal to Wn minimum model, whose primary field is specified at this capital N is capital M. And this is equivalent to the, in fact, arises from the color algebra of A n minus 1, A m minus 1, just diagonal theory. Okay. So that as a higher rank generalization, one can just obtain the S and T matrix that acts on this the expression divisor, which can be identified the Wn minimum model. So therefore, so the Hilbert space coming from here is one-to-one correspondence of the primary field of this Wn minimum model. Okay. Or Groton, it's called, it's more like a fancy word, it's called Grotonic group of modular tensor category of this minimum model. It's a fancy word, but it's just the number of the primary field is identified dimension of this Hilbert space coming from here after geometric quantization of this guy. To long story short, in fact, these mathematicians also studied from the Daha or Chernyak algebra, and this quantization of this, how to say, geometric quantization of this Lagrangian, out of it, one can get the so-called bottom row of the n, m torus knot homology. It's just a so-called lowest A degree of n, m torus knot homology. That is also some here vector space. But that's a different issue. But out of this Lagrangian inside of this higher rank SL and C flat connection of the one functional torus flat modular space, so one can connect seemingly different vector space. One is coming from this representation of Daha, the other coming from the minimum model, the other coming from torus knot homology. So they are all coming from this extension divisor or Lagrangian inside a modular space Higgs bundle. And in fact, this finite dimensional vector space is one-to-one correspondence of so-called C star fixed point of the Hitchin modular space of this wild Hitchin modular space of coming from here. I mean, once you impose this condition, one can connect to Saga theory, and in fact, this finite dimensional vector space is the one-to-one correspondence C star fixed point of Hitchin modular space. Any question at this moment? So therefore, once you start connecting 2D physics and 3D physics, one can have a surprising connection between PSA to the action on the vector, some finite dimensional vector spaces. One is minimum model, one is Daha representation, the other is torus knot homology. Any question at this moment? Otherwise, I will move on to 4D physics from now on. Okay. So the lifting 3D will give you how to say some identification of Daha module and then some primary field set of primary field minimum Wn minimum model. That is another one surprise. And if you live to 40 physics, you can get another surprise. Okay, so let's move on to 40 two-star theory. We'll try to connect to the Daha and the 40 two-star theory. So the ingredients is actually in 40 is a class S theory. And then class S theory, most of many audience know, it just wrap the Riemann M5 brane on some Riemann surface can have the ramification. So M5 brane is labeled by ADE, and then the number of M5 branes. And if you wrap the Riemann surface, you get the so-called 40 2 theory that is constructed by brilliant people, the brilliant physicist, which all of you know. This C is called sometimes Gauss curve or like a UV curve. And here, you consider the cotangent bundle over this Riemann surface, and then so-called spectral curve or IR curve, or the cyber-Witten curve is some round-bar curve of C, which is obtained by embedding of this cyber-Witten curve on a T star of C. So this is called really Hitchin system. This Hitchin system really describe the both UV and IR behavior of the 40 2 theory. However, 40 2 theory is a bit more subtle. One has to include so-called additional discrete data. So people just call it the class A theory is just specified by Riemann surface and number of M5 branes and then ADE type. But that's not true, but one has to so-called include so-called some discrete data coming from some global structure of the that line operator in the spectral line operator depends on global structure of the so-called gauge group and so on. That is specified by the discrete data, which I'm going to explain. This is the L. It's just obtained by so-called coming from the so-called simplex basis of Riemann surface. So given a Riemann surface, one can have one cycle, and one cycle have so-called splits into the A cycle and B cycle, as I mentioned. So you have it's like A cycle is alpha, I call it alpha 1, and B cycle I call beta I, and they satisfy intersection form, like alpha and beta intersect non-trivially, but the other, the self-intersection form is equal to 0. That's called so-called simplex basis, which is not unique. Which is not unique, but that will give you some. And if you consider the center, first homology group whose coefficient the center of this ADE, one will get so-called lattice, some simplexic lattice you will get. And then here you have to, this discrete data is just coming from so-called maximum isotropic sublattice, which is very similar to Lagrangian condition. But even though it's complicated, I'm going to give you some explicit examples, so don't worry about it, don't intimidate about it. Anyway, so to specify 40 equal to 2 theory, one has to impose so-called discrete, include so discrete data come from this simplex basis. And in fact, this Coulomb branch of 40 equal to 2 theory, once you put the cross S theory on S1 cross R3, Coulomb branch is given by so Hitchin modular space given from this Riemann surface C and gauge group G, but you have to divide it by so-called divided by this discrete group action, and this discrete group acts on the this Hitchin fiber like a freely. So therefore, this complete integral structure is preserved. So therefore, so the Coulomb branch is some quotient of the usually quotient of Higgs homogeneous space, but it can just project to the so-called whatever trace of phi square, or in physics language you just project the U-plane, and whose preimage is generated in torus. So it's a complete integral system. But the important thing in generically, Coulomb branch on the S1 cross R3 of the class set theory is different from the Higgs homogeneous space or homogeneous space of flat convection, GC flat convection. So you have to co-simplify discrete data. I just give you an specific example of the for the n equal to 4 or n equal to 2 star theory. So as you know, many of you know, for the n equal to 2 star theory is just obtained by the M5 brane wrapping on the once function torus. Okay, so our favorite once function torus. Out of it, one can construct for the n equal to 2 star theory. So a 2 star theory is the n equal to 4 to n equal to 2 star. We just put some mass of the adjoint hypermass. So discrete data we will impose as follows. So since we have the torus as a base curve of the Hitchin system, so you have again meridian and longitude, okay? And then the center of SU2. So you have to consider the center of the gauge group is in fact Z2. Z2. So therefore, you have the as a simplex from simplex basis of the Riemann surface, you get the Z2 plus Z2 lattice. Okay, yeah, essentially you have this kind of lattice, this kind of lattice, and then L you can choose is the vector on in this ladder. So once you set the L as some meridian direction or sorry, which direction? Sorry, I call it this one is y direction. I don't know why it's y direction. Anyway, whichever call it. So in this direction you get the L as this direction you get the SU2 for the n-2 star theory. But if you take different L, you get the SO3 for the n-2 star theory. Depending on this, you pick the X direction or Z direction. I call it this is Y direction. I'm sorry for the different convention from the previous slide. But anyway, depending on the choice of vector you pick, you get a different n-2 star theory. And SO3 theory, in particular, SO3 theory have a discrete set of angle, and theta equal to 0 is equal to plus, and theta equal to pi is equal to minus, which is distinguished by so-called Stiffy-Whitney class of the Higgs bundle. And in fact, as you can so easily see, you can easily imagine from this construction. So since torus receives SL2Z action, to the SL2Z action, so therefore this SU2, sorry, SU2 theory and SO3 theory, SO plus minus theory is indeed shuffled by this SL2Z action. So there's a folklore of the how to say for the n equal to 2 star theory of type A1 receive the automorphism SL2Z. That's not the case, in fact. They are actually, under the SL2Z, they are shuffled. SO3 and SU2 are shuffled, like this. And then, as I mentioned previously, so the Coulomb branch and the Higgs homogeneous space are related by the discrete group coming from this maximum isotropic lattice. And then once you set this discrete group is indeed appear from in the Daha automorphism. It's called Xi in Daha automorphism. And this one is identified C1, this one is like C2. Okay. So therefore, to go from Higgs homogeneous space to Coulomb branch, one has to take a quotient by this discrete group. Once you set this y direction, that's why I call it this y direction. To get the SU2, you have to quotient back C2. The y direction, you have to quotient. And then, if you take a quotient back C1, you get the SO plus Coulomb branch. And for C3, you get the SO3 minus Coulomb branch. Okay, that's how the relation between Coulomb branch and Hecke homogeneous space or flux connection. Any question at this moment? Fine, let me move on. So how the geometry look like? So the geometry of the Coulomb branch is as follows. So go from SU2, the Higgs bundle module space, Higgs module space, to the Coulomb branch. One has to take C2 portion. And usually this C2 is indeed acts as follows. So C2 is a Z2. So you have, if you look at this singular fiber, you have two bananas, I mentioned, like this way. And C2 is indeed acts as a 180-degree rotation, 180-degree rotation. And then this one is 180-degree rotation. I think the opposite is better. 180-degree rotation. Okay, so it's so therefore, once you do the 180-degree rotation, so it's like you start with sphere. Banana is the topological skin of banana is topological sphere, and the 180 rotation is just like 180 rotation. If you quotient that, you get something like that, like this kind of geometry. You have A1 singularity appear in both sides, south pole and north pole. Okay. So therefore, once you take the quotient of C2, in fact, you have the two A1 singularity show up in a singular fiber. So here, so the fixed point of this C2 is indeed this double point, which means at which the two banana meets. So this two double point becomes really A1 singularity. Okay. On the other hand, once you go to the other fiber, in fact, this C2 acts as a just how to say, like this way. C2 acts as a swap sigma 5 and sigma 6. And then here is sigma 3 and sigma, sorry, not sigma, U5 and U6, U4 and U3. So therefore, by C2, they identify and become like this way. It's just only single compound, single banana will show up. They just self intersect. Okay. Only. So therefore, here you have this kind of geometry show up. The other singular fiber, you have this kind of geometry show up. In fact, this one is identify I1 singularity. And this one is look like the previous I2 singularity. So previous I2. But here, since we have I1, so this is indeed some special limit of the I4 singularity. I4 is a 4 type. So if you have a middle guy, so this is I4 singularity, and if the middle, this two sphere will shrink to the point A1 singularity show up. So therefore, you have I4 and I1 and I1. So these are the Coulomb branch geometry for SU2. And this I4 singularity is in fact the quark singularity of the Fourier two-star theory. And this I1 singularity is the, in fact, monopole and dion become massless singularity. So therefore, this singular fiber on Coulomb branch, it has some meaning in physics. So this I1 singularity is the monopole and dion singularity, and this guy is the quark singularity. Once you set the mass of the hypermultiplet to the infinity, this guy goes to infinity. So therefore, what's left is these two dion and monopole singularity, which is appear in the cyberwidth and on pure melt. So it's a very, very consistent with the several times solved. Any question at this moment? Fine. So then one can just take the other quotient, so complement of this maximum choice of the discrete L, one can get so-called SO3 SO3 Hitch modulus space or SO3C the flat connection modulus space for flat connection. Okay. So the complement of the C2 is C1. So one can just go farther from Coulomb branch to SO3 Hitch modulus space. So now C1 is just identify this Euclidean component, this Euclidean component. So therefore, single how to say, Euclidean component will show up like this. And then C1 acts on like 180-degree rotation on this fiber. I want singularity on both sides, and that so therefore at this double point you get the A1 singularity to show up as the like the reason is as before. So therefore you have the similar fiber, C fiber show up, and in fact this is some degeneration of the degeneration of this fiber. Indeed, degeneration. Sorry, what I'm drawing is something strange. Degeneration of this I2 singularity, but this middle guy, volume goes to 0. Middle guy, volume goes to 0, you get the A1 singularity show. Therefore, even though there are 3 singular points will show up, there are I2 singular fiber, in fact. So some particular limit of I2 singularity, I2 singular fiber for these 3. So if you compare between original SU2, you have I2. But if you go to SO3, you also have I2. Even though there is a singular Duval singularity show up, but that's very common feature in the geometric language. So as you might have known, SO3 is Lagrange dual of SU2, but if you take the Lagrange duals in Hitch modulus space, the quadrilateral type of singular that do not change, even though the shape will change. So from SU2 to SO3, one of the related component needs to go to 0 volume limit, but the type of quadrilateral singular fiber won't change. Any question at this moment? The analysis of modulus space, we do not need Daha, right? Yes, but from now on, I will connect to Daha. Well, from now on, I will connect Daha. So we know that if you quantize, do the deformation quantize of this guy, you get the spherical Daha. But here, to get the deformation quantization Coulomb branch, we need to take a quotient with this discrete D2 cross D2, which is in previous slide called C. So the deformation quantization of Coulomb branch is indeed equivalent to the so-called algebra line operator in the presence of omega background. This was argued by Gautam Naitsky. Also, this Japanese group. Now, how to get this deformation quantization? So you just consider S1 cross R3, but you turn on the omega background. So omega background here. Okay. So therefore, everything local R3 is this R3. If you turn on omega background, everything localized into the axis omega background. Therefore, line operator wraps on this S1 direction, but the position is localized to the origin of the axis of the omega background. Therefore, once you just try to move this position of line operator, it must hit. So that, for instance, Wilson loop and Fuchs loop or Dionic loop and so on. Once you move around and to the other direction, it has so the order really matters. So since they once you turn on the omega background, so therefore once you turn on omega background, the algebra line operator becomes non-commutative. Whereas once you forget about the omega background, the position of the line operator can anywhere in R3. So therefore, you can freely move without hitting all the other. So therefore, once you forget about Q goes to one limit, the algebra becomes commutative. So that is very, very equivalent to what we saw from in the Daha side. And then again, so to connect to the 2D signals, she changed the question. BCC boundary condition is really coming from tip of or like axis of omega background. So that you just you start with Fudan two-star theory, and the compact file on S1 here with the S1Q. S1Q is really U1 rotation around the omega background. Oh no. So if you compact file on this S1 cross S1Q, you get the 2D sigma model, and then this S1Q swipe the R3, and what's left is this strip with boundary condition here. And algebra line operator is really coming from this axis omega background that will give you BCC condition here. Therefore, if so the quantization Coulomb branch is really is equivalent to algebra line operator that is argued by Latam. And using that one, so one can just predict that this quantization of Coulomb branch of SU2 is indeed C2 invariant subalgebra of Strecker-Daha. Since we take the quotient from Hitchin modular space to the Coulomb branch by C2, so algebra has to be invariant on the C2. Okay, C2 is, as you recall, C2 is x, y goes to minus y. Okay, so therefore it has to be invariant this action. So therefore, this SU2 quantized Coulomb branch, deformation quantization Coulomb branch algebra line operator is indeed generated by small x, which is x plus x inverse, but in fact, you have to have a y squared instead of y. Because I mean, y plus y inverse is not invariant under this C2. You get the minus sign. Whereas if you take a square, it doesn't matter. The sign doesn't matter. And if you look at this one, this is indeed adjoint representation SU2. Adjoint representation SU2, character is SU2. Adjoint representation. This is, whereas this guy is the character of the fundamental group SU2. So therefore, adjoint line operator is generated by fundamental Wilson loop and the adjoint Wilson loop. In this SU2 theory, you cannot have a fundamental two-hoof loop here. Sorry, here, why is two-hoof loop? Sorry, I should have mentioned this is not Wilson loop. This is the two-hoof loop, but in adjoint representation. X is the line operator coming from median, which is Wilson loop, and from longitude twice is adjoint two-hoof loop. So these are the SU2 line operator. And likewise, the SO3 plus and SO3 minus, you get the different quotient. C1 invariant subalgebra or C3 invariant algebra. In taking different discrete quotient, you get a different line spectrum or line operator. So the SO3 plus, you have a fundamental truth loop, but you have a adjoint Wilson loop. You cannot have a fundamental Wilson loop in SO3 plus. And so on. So SO3 minus, you have a fundamental dionic group, but Wilson and truth are adjoint. Any question at this moment? Okay, so now, so once you specify discrete data, one can relate the Strecker-Daha and the algebra line operator for the Hecke two-star theory as an invariant subalgebra by this and discrete data. One can just consider the different way of looking at the algebra line operator. So this is a different way of looking at the algebra line operator. So here we consider that a line operator R cross R3 is a spacetime for 3 for the n equal to 2 started, and put the line operator in the first R direction and at the certain point in R3. And here this system is really the R3 in here, and this blue dot is the line operator. So I just suppress this the first R direction. So this guy is indeed R3 in second direction, and this blue one is the line operator. To go from the to see the effective line operator, you have to see the R2 inside of R3 and to the R2 inside of R3. There is something occur because of line operator here. So to see this effective line operator, you have to consider so-called rabiolo. So this upper C, a lower C, and then it just quotient by C star. C star is this R C, and omit this disk direction. So this is C star. You just identified. So this is look like a really labiolo in the Italian whatever cuisine, pasta, whatever you call it, the special kind of pasta. So once you so here you have R3 here, R3, and then this R direction, and this line operator, and around the line operator you have a labiolo. So this really look like labiolo. So you just compact find a labiolo, you get the so-called the boundary condition coming from line operator. And then here, this model, local model line operator is considered many people, some mathematician, how to say, Berkovich, Finkelberg, no, sorry, Bezirkanko, Finkelberg, Markovich, and then Brabham, Finkelberg, Nakajima recently. Not recently, anyway, already like a few years ago, more than 5 years ago. And this model is considered in physics and in comparison with them. And for boundary condition coming from line operator, for Wilson loop, you get the so-called BBB brane in the Hitch modular space, and a BA brane for the Hooft operator. But in fact, Hitch modular space coming from this labiolo. And then, in fact, if you look at the complex section I, everything is in B brane. Okay? So therefore, in B brane in mathematics is called so-called categorical coherent sheet. And this Hitch modular space labiolo, so there's a special name called affine Grassmann-Stein variety, which I'm not going to go into detail, which can be constructed from the really this local model of this C star. It just can be constructed from here. That is can be constructed from loop group or like a formal series power series. I'm not going to go into detail. And then if you consider this affine Grassmann-Stein variety and consider B-brane category here, that is really the category line operator in 40 n equal to 2 star theory. If you take the Grothendieck ring of this category, you get the so-called algebra line operator, which is indeed in fact the function of the modular space of flat connection quotient by discrete data. So as I mentioned, so T cross T mod W, TC, actually TC, is a modular space of flat connection of the torus. And if you take the discrete data, quotient of discrete data, this becomes one fifth part, it becomes the some dual maxima torus and W. So that's why you have a check here due to the discrete data. And then one can naturally turn on the omega deformation and the ramification parameter T and Q. That will give you some algebra line operator in the presence of this deformation Q and T. that is there's some invariant part of the spherical Daha. So that's another way to get the algebra line operator. And unfortunately, I'm running over time, so I think I'm going to. I'm not going to go into detail. One can also include so-called surface operator. So if you include surface operator, so far we only talk about spherical Daha. But how about Daha itself? The Daha itself can be obtained from the algebra of the line operator on the surface operator. So you consider the R cross R2, and the surface operator is here, and then the line operator is the first component, and the surface operator is the only first two are component, and then you can consider the algebra line operator on the surface operator. And then we can consider corresponding local model for H module space and so on. So because of the surface operator, so this that one is surface operator. Because of surface operator, there is some ramification on the Rabiolo up here. That will replace the affine Grassmann sign variety, affine flux Steinberg variety, which I'm not going to go into detail. If you take the corresponding operation, the whatever Grothendieck group and so on of this category, you get the Daha itself. And Daha with take some caution. And this model was already considered Basrot in a long time ago. So this can be understood the algebra line operator on the surface operator. And then one can generalize this kind of stuff to connect to the 3D story again and so on. So in previous case, I don't consider any surface operator to connect the 3D story to and 2D. But if once include surface operator, this surface operator will give you some other ramification here in the zero of the some north pole of the sphere. So therefore, you can connect to the more general algebraicity once you consider representation of Daha itself. This system is already considered by the people group in Tsinghua last year and so on. And then anyway, so I'm not going to go into detail because the time is over. So one can see the more sophisticated relation between chiral algebra, just diagonal theory, and set to the action coming from this chiral algebra, and then Daha of the set to the action acting on finite dimensional representation of Daha itself. And the corresponding geometry has been considered these mathematicians. Okay, thanks for listening and sorry for going over time.
Thank you, Letus. Thanks, Professor, again, for giving this really nice. Are there any questions?
Yes. Any questions? Okay.
Yeah, it's okay. I think you can take some time to explain this slide. I think that's the main result. So maybe we should say something else.
So yeah. So the one comment is that the even if you take q goes to one limit, Daha itself is no longer commutative because I mean this can be seen that if you have a surface operator, I think I should use the red one for surface operator, and you can consider the algebra line operator on the surface operator, even if even without the presence of the omega background. Once you try to move the line operator on the surface operator, the line operator hits the other line operator. So therefore, the order really matters. So therefore, the algebra becomes non-commutative even q goes to one limit. So therefore, Daha has this kind of property. That's one comment I can make. And once you include this surface operator, so this is in fact the codimension 2 defect coming from intersection and fibrine. So intersection and fibrine provides some regular puncture at the north pole, in addition to the South irregular function we consider in the 3D story. And this is more general algebra theory. And then, so from out of here, one can construct so-called modular tensor category or like an essay to the action of the chiral algebra. And then these people at Tsinghua find that the essay to the action on this chiral algebra is indeed the same as the essay to the action acting on the finite dimensional module of the Daha itself. It's not the spherical Daha, it's the Daha itself. And in our story, we consider only spherical Daha that can be obtained by just doing the Sokolov reduction of this affine algebra. And then this algebraic side is really connection is coming from so-called affine Springer fiber, which is the anyway some finite dimensional variety inside this Steinberg variety affine Springer. So this is the infinite dimensional some modular space or infinite dimensional manifold, but one can find some finite dimensional one, and then if you look at the C star fixed point, and then there's a one-to-one correspondence, and so on. If you consider Hitching space or this wild function and look at C star fixed point, there's a one-to-one correspondence that is given by this brilliant mathematician at MIT and so on. These are the recent development after our paper, and then we can consider the future direction. For instance, with my students at Fudan, we consider so-called sphere with four puncture. We can construct a similar story by using the Branes quantization. One can consider more algebra line operating, more general cross set theory. So you can, how to say, increase the genus, like a genus 2 case or genus CGN case, and so on. This kind of stuff nobody has studied yet. And also this people in Tsinghua find, I mean, from out of here, one can just, out of algebra theory, one can construct a chiral algebra, and some algebra theory has the Higgs branch. And then what's the relation between Higgs branch of algebra theory and then Coulomb branch, which is the Hitching modular space of this irregular Hitching system. And that is like this guy study the so-called people called 4D simplex duality. But it's just still like it's not mathematically well formulated, even not like 3D simplex duality, but they just study like some evidence of 4D simplex duality in this setting. But there's lots of interesting things going on between geometry, algebra, and physics. I hope people just understand the very intricate connection between these three different subjects. Yeah, so that's I wanted to explain. But yeah, sorry for going over time.